Protorikis. In the previous video, we looked at how SSD KV caching works in OMLX, how it compares to llama.cpp and Ollama performance-wise, and how it crashes my macOS near the memory limit. And during those experiments, I really enjoyed that Ollama, and in fact the underlying Apple MLX framework, supports running NVidia's NVFP4 quantization models. It's really elegant, as the same model weights are used on NVIDIA's CUDA and Apple's MLX. And as we saw, the performance increase of running NVFP4 on MLX compared to llama.cpp GGUF models was substantial. Check out my previous two videos for more details. So I decided to switch my daily workflow and instead of the proven 4-bit GGUF quants, try these new NVFP4 models. But I really need to know whether they are as good as advertised. So in this video we're going to zoom in on NVFP4 quality. Are these models as reliable as GGUF ones? Or does faster performance come with a trade-off? By the way, some of you came from Alex Ziskin's video. Warm welcome to the channel.
Or more accurately, I was heavily inspired by this channel. Protorikis.
Yes, Protorikis.
6,000 subscribers? Everybody should go and subscribe to him right now.
Thanks, Alex, for the warm shout-out. So let's understand what's so special about NVFP4, and then run a memory quality benchmark. The results are really interesting. After you train a large language model, you get 32-bit floating point numbers. For a 35 billion parameter model, that's 35 billion floating point numbers, which describe the resulting neural network. And a single 32-bit floating point number can represent over 4 billion possible values. So what happens when you use 4-bit quantization to compress these weights? This is how a 4-bit signed integer looks like in memory. First bit tells you whether it's positive or negative, and the remaining 3 bits encode the actual number. This way, a single 4-bit integer can represent only 16 possible values. Compare that to those 4 billion of FP32. I actually find it quite mysterious that these models work so well, regardless of such extreme compression. It's a whole dedicated research area. Did you know that there's work going on mere 1.5-bit quantization that seemingly matches 16-bit floating point precision? Either way, the trick that Q4 quantization does is that it breaks those 35 billions of parameters into blocks of 32 numbers. Though that's a bit simplified. In reality, those blocks can vary in size depending on the layer, and K-quants like Q4 K M group those blocks into superblocks, but you get the idea. So when you look at a block, you find the largest absolute value in it, and compute its scale by dividing by the maximum value of a 4-bit signed integer, which is 7. Finally, you simply divide the original weight by this scale, round to the nearest integer, and voila! You get the quantized 4-bit number. When you think about it, it's quite simple, isn't it? And overall, it's quite fascinating. At the end of the day, these models are just billions of numbers, compressed into even smaller numbers, and yet they can write code and hold a conversation, more or less. And here's the issue. When you dequantize these compressed weights back into their floating point representations, naturally you get the drift. That's called quantization error. And these big errors of 27% are edge cases, where the model is working with the numbers that are quite off from what the original training produced. And that can lead to subtle mistakes in reasoning or hallucinations. So how does NVFP4 quantization handle this? It's actually both similar and different at the same time. Instead of taking 4-bit signed integers, it uses 4-bit signed floating point numbers. Just like in Q4, the first bit tells you whether it's a positive or negative number. But then you have 2 bits for the exponent. That's the power we raise a 2 to. 2, 2. And 1 bit for mantissa. Like with a 4-bit integer, this also gives 16 possible values, but they are spread non-uniformly. More precision near 0, less at larger values. And as we'll see in a minute, that's important. This is the actual bit-to-float conversion formula if you're curious. University stuff. And the trick that NVFP uses, it breaks those 35 billion parameters into blocks of 16 numbers, as opposed to 32 like in Q4. And it computes the scale of this smaller block. On its own, that's more precise. However, it's using 8-bit floating point to store the scale number, as opposed to 16 bits in Q4. And that offsets the benefit of the smaller block size. And this is how FP4 quantized values look like. Pause here if you want to drill down. In this specific tiny example, Q4 actually outperforms NVFP4. But let's add more numbers to this batch. As you can see, when weights cluster in that small but not yet zero range, FP4 wins. And in practice, most model weights are clustered near zero. This is the bell curve of model weights. And NFP4 may have some advantage here. So, what do we see from this architecture? Smaller blocks means more precise scales. But scales are at lower precision, which offsets the above somewhat. While the float values provide non-uniform precision, they're more precise near zero, where most weights cluster. And NVIDIA says its quality is close to FP8. Wow, and The fact is that we have limited independent comparisons. And it's genuinely hard to measure. But let's try to do that and see the results. If one thing is clear, when you run NVFP4, it will behave differently compared to Q4, even though both are using 4-bit weights. By the way, one comment about size. I mistakenly thought that Q4 K M model in lmstudio is slightly larger than its NVFP4 variant. But it isn't so. Apparently, lmstudio calculates vision encoder file into the size shown, which make it look larger. In reality, both quantizations are similar in size. Don't get fooled by this like I did. Let's run a memory recall benchmark, which I used in the previous videos when comparing Llama 4 versus Qwen 3.6 models. I'll leave a link to them in description. I find this test especially interesting as it gives real usage perspective. Though I think we'll need more benchmarks for strong conclusions. By the way, if you're enjoying these deep dives, leave a like and subscribe. Let's benchmark two Qwen 3.6 NVFP4 models. Let's begin with 35B A3B Mixture of Experts one, and afterwards look at its dense brother 27B. I'm starting Ollama server here with a keep alive flag. Not sure it works though. That's one of the things I don't like about Ollama, is that it offloads my models without asking. Back to benchmark. It's loading 95,000 token JavaScript file and asking the model to reproduce the first 20 lines after an opening brace of a certain function verbatim. Fast forward and the prefill finished. Note that the prefill speed is about 30% faster on this MLX NVFP4 model compared to llama.cpp Q4. That's the main reason I'm looking at this at all. While the next 15 prompts for different functions are almost instant. That's the power of properly working KV caching. Even though we're sending that JavaScript file with each request, its computed KV cache values are reused. Perfect. And we have the first model results. 5 tests failed, but let's look at them in detail. This function is good. This one good. Here model added function signature, even though we asked the model to print code after opening brace. But we can consider that pass. Same here. One more. Really interesting that 35B MOE model is doing this. In those previous benchmarks, only the 27B dense one was prone to this behavior. First real failure. The model failed to return part of the function body and improvised a non-equivalent return statement in yellow. In JavaScript, this returns only the query station list string and not both values. All the other functions are correct. Let's compare this run to the Q4 K M model that I ran in one of those previous videos. Q4 model didn't add those extra function signatures, so the summary is cleaner. That getWiFi function was returned correctly too, but it failed on this long name function where NVFP4 passed. So both of them have only single real failure. Importantly, in total NVFP4 model returned 258 correct lines, compared to 245 of Q4 K M. That's a positive metric. Now let's run the benchmark on the dense Qwen 3.6 27B model. Starting the test and skipping recording, as 27B is much slower model than 35B A3B. Fast forward and we have the results. What? This function returned 2,621 extra lines? First time I see such results in this benchmark. Let's take a look. Wow, these yellow lines are all those extra lines. So the model simply didn't stop generating, even though we asked it to return only 20 lines of code. Let's look further. This function is good, just return the signature without us asking to. And most other functions are with extra signature line as well. Consider them passed. Here is a real failure in Get Wi-Fi station list. The model forgot one of the closing braces. And another one of exactly the same kind. Very interesting consistency in these two failures. The other functions are good. Looking back at results, we have two real failures and that one huge generated output. Let's compare this to Qwen 3.6 A3B Q4 run from an earlier video. Here we actually find some similarities. Both of them returned function signatures, though we asked not to. There are these extra 1 lines in the summary. But NVFP4 had two real failures, where it missed the braces. And Q4 had no missing lines, it was one of those almost perfect runs. But it had an issue which is not visible here straight. It's not very obvious, but you can see that it is missing one function from the list. That's because it entered a degenerate loop and never finished generation, and I had to remove it. And now that I think about it, it is actually very similar to that runaway generation of NVFP4 model too. Only the function is different, and NVFP4 was able to finish it. But just look at this. NVFP4 returned 300 matching lines. And I just realized that this is an absolute record for this benchmark. Didn't expect that. Overall, I'm really surprised that MOE35B model had less errors than its dense 27B one. In general, dense architecture is stronger for this task. Yet I'm quite happy to see this, because it's the MOE one that I'm using on a daily basis due to its speed. And only with one failure and more matching lines than Q4 K M model, I think I'll keep testing NVFP4 further. Are you running NVFP4 models? How well do they work for you? Or do you prefer other formats? Don't hesitate to leave a comment below. I hope you found this video useful. Come back for more. I wish you a great day and see you next time.